this is VLSI data conversion circuits, lecture 37. In the last class we looked at dynamic range scaling of the loop filter, so that the integrators in the loop all kind of saturate at about the same input level. This way not one single integrator prematurely limits the performance of the loop. Okay. The next subtopic that I wish to discuss is the practical issue of how one goes about simulating a delta sigma loop. So, with the discrete time modulator, one can think of the loop filter as being a discrete time system with two inputs and one output, and the output is quantized and fed back. Alright. So, this is a linear filter and can therefore be represented by the state equations, the difference equations which can be recast in state space form, alright, and the state matrices are given by A D, B D, C D and D sub D, right, and the state formulation is that the set of states x, please note that x is a column vector at instant n plus 1 is linearly related to the set of states at instant n plus B D times the inputs to this linear system, which are u and v. So, this is a 2 row 1 column system, right, and y of n is C x plus d times u and v, right. So, in general the AD matrix will be an n by n matrix, it is a square matrix. BD in our case will be a what will be the dimensions of BD? N cross 2, CD n cross 1 cross, okay, because you have only one output, okay, and DD 1 cross 2, all right. And so, if you concatenate these matrices together, it will form how many columns are there? If I concatenate AD and BD, how many columns are there? n plus 2 columns, and if how many rows are there if I concatenate BD and BD? BD has got n rows, n plus 1, correct. So, if you put AD, BD, CD and DD in this fashion, you will get a big matrix which is n plus 1 cross n plus 2, right. And if you know the order of the system, given this composite matrix AD, BD, CD and DD, or if I call this A, B, C, D sub D, and if I know the order of the system, then I can find everything, right. You understand. So, this is a useful way of passing A, B, C and D as one matrix rather than 4 matrices. Anyway, this is an aside. Okay. Now, you see the simulation is quite straightforward. Once you know the present state, right, and you know A, B, C and D, and you know the input, you can find the next state y, okay, that is quantized, and that becomes the next input, correct. And as you have all played around with the toolbox, if normally implemented in MATLAB, this would require a lot of for statements, right, because I mean this is a feedback system, so you can't run it parallelly, okay, at least in a straightforward way. So, what the toolbox does is implements this loop in C, so that the computation is very fast and interfaces with MATLAB, and therefore, the simulate DSM routine is actually very fast and very functional, right, where you specify the loop filter in state space form, for instance, give a set of random initial conditions for the loop state variables to begin with, and it does the rest. It will also give you the maxima of the state variables, okay. And what is the utility of the maximum of the state variables? I mean this is the simulate DSM routine only simulates a linear loop filter, but the maximum of the state variables can be used to advantage to scale the coefficients inside the loop filter, so that the outputs of each of the integrators are confined to some limit, right. So, now the problem that we are trying to address is how does one simulate a continuous time loop filter, right. The situation is actually quite similar in the sense that okay. This is a function of time and this is sample. The loop filter now is a linear system and can therefore be described by a state space formulation. And what is the state space formulation? X dot is AC times x plus BC times u, and V, and y is nothing but Cx plus d u1. Is this clear? Now, the remarks we made with respect to the dimensions of A, B, C and D hold here also. Okay. But one thing we need to be aware of is that the u and the v here are now functions of t. So, to make that explicit, let me one thing to observe, however, is that we are really only interested in the samples of the loop filter output, because that is what determines the a quantized version of that is what the output sequence is. We would be interested in finding what the output discrete time sequence is for a given continuous time input u, correct. So, we would like to find out therefore only the outputs of the loop filter at discrete instances of time. We are not really interested in the output of the loop filter for all time. So, the question now is, can this be exploited to simplify the simulation of the loop? Do you understand? Normally, we would have what we would have to do otherwise would be, given u of t and given v of t, we have to integrate this set of differential equations which are linear because the system is linear, and generate y of t, correct, and then sample it and use that sample value, quantize it and feed it back. But it seems like an awful waste of effort, because you are computing the output of the loop filter for all time and only taking samples. So, the question is, can I be smart about it and simplify things if I am only interested in samples of the output to begin with. Is this clear? Okay. So, what one should observe are a couple of things. One, of course, is that v of t is v of n passed through a pulse shape p of t. All right. And for most practical purposes, these pulse shapes are either the NRZ pulse shape or the RZ pulse shape, okay, or the exponentially decaying one. I will show you the method for an NRZ pulse shape, and the rest of it is actually quite straightforward and works in a similar way. The input, on the other hand, what do we say? The input is slowly varying because the system is an oversampled one, right. So, the input can always be modeled as approximately a first order held waveform. So, the input being slowly varying, all right. Okay. So, as far as the input is concerned, because it is slowly varying, since we are dealing with an oversampled converter, one can think of it as a sampled version u of n driving the pulse shape, which is actually an NRZ pulse, correct. Therefore, if this pulse is also an NRZ pulse, we now have a linear system whose two inputs are basically u of n and v of n with NRZ pulse shapes, and this is y. Of t, we are actually interested in y of n. Is this clear? Now, let us try and see what the output. I mean, please note that as far as this system is concerned, the one drawn in the green box, this is still a discrete time system, right. So, the inputs are discrete time sequences, the output is a discrete time sequence. So, if we are able to find therefore the equivalent discrete time system, you understand, if you think about this green box, two discrete time inputs, one discrete time output, the box is linear. So, one should in principle be able to derive a discrete time equivalent of this continuous time state space system, and once we do that, it is just a matter of using the delta sigma delta toolbox to simulate the continuous time modulator. Is this clear? So, if you have an input, so x dot is AC times x plus B BC times U and V, right, or U of T and V of T, but now the U of T and V of T are slightly different in the sense that they are held, both U and V are both held constant between adjacent sampling intervals. Is this clear? So, if this is the set of differential equations, what is the solution to this? Let us say the initial condition at time n was some x naught, okay. We need to find what the states will be. Solving the differential equation is nothing but finding the states, right. And how do we derive the state, I mean what are the state equations of the discrete time system we are after? The state formulation is telling you how the next state relates to the previous state, that is how you get AD and BD, right. So, in other words, as far as the continuous time system is concerned, given an initial set of states x naught, right, and given the input to the system, right, we would like to find what the output or what the states would do after 1 second. 1 second is, I have assumed that to be the sampling rate. Is this clear? Okay. So, in other words, the loop filter which is continuous time has an initial set of states x naught. I would like to find what the state will be at n plus 1. Okay, rather than call it x naught, I suppose it is a better thing to call it x of n. All right. So, what will be the state variables at n plus 1? There are two things happening here. If the input was 0, you would get the 0 input response, and what would that do? Okay. So, it turns out that the impulse response of this set of differential equations is e to the at ac times t, right. So, if you had an initial condition x of n and no input at all, the states would follow the trajectory e to the ac times t times x of n. So, at t equal to n plus 1, what will happen? In other words, if you I am sorry, what I meant was, so t minus e to the ac times t minus n. Okay. So, at t equal to n plus 1, what do you think will happen? The states will have changed by e to the ac times n plus 1 minus n, which is e to the ac. Okay. So, x of n plus 1 will consist of two components, one which is the natural response of the system or the transient response, where the states decay with as e to the a c times t minus n, right. I mean, you are all familiar with this from basic circuits, correct. Let us say you have an RC circuit, the capacitor is charged to some voltage V naught, and then you let the circuit go. What will happen? The capacitor will attempt to discharge through the resistor with a time constant tau, correct. So, after a time of 1 second, it will be the initial voltage multiplied by e to the minus t, correct, and it turns out minus t by RC, right, and if you do the state space formulation, you will get exactly the same thing. But there is also a forced response, because the inputs are trying to excite the system, correct. So, the forced response will be, you have a bunch of inputs and you have a set of impulse responses. So, once you know the input and the impulse responses, the output is nothing but the convolution of input and the impulse response, and what we are interested in is this convolution integral, because we assume that you can, for all practical purposes, whether you start at n and go to find the output at n plus 1 or start from 0 and go to 1, it is the same thing, correct. So, this is a convolution which is integral 0 to tau, the impulse response e to the a c t minus tau, right. Please recall that h of y of t is nothing but h of t minus tau u of tau d tau integral 0 to t. This is the standard convolution integral, correct. So, you want the output at the after 1 second. So, e to the AC 1 minus tau, correct, BC times say u of t v of t d tau, u of tau, sorry. Okay. But within this interval, what are u and v? They are u of n times constant 1. Similarly, this is v of n times a constant 1. So, if you think of this as you can also write this as 1 minus tau BC1 into u of tau d tau plus integral 0 to 1 e to the AC to 1 minus tau BC2 v of tau d tau, where BC is nothing but BC1 BC2. All right, and u of tau and v of tau are both, I mean you can think of them as u of n times 1, and similarly this is v of n times 1. Is this clear? Now, this integral, both these integrals are of the same form except for change of variable names. So, let me just evaluate this character. This is v of n e to the AC integral 0 to 1 e to the minus AC tau BC2 d tau, and what is please note the v of n is a scalar. This is e to the AC times its minus AC inverse, okay, e to the minus AC times tau times BC2 and this has to be evaluated from 0 to 1, which is v of n e to the AC inverse, and this becomes I no 1, right, it is identity matrix minus e power minus AC, correct, into BC2, and because AC inverse and e to the AC commute, I can flip the order of multiplication and push e to the AC inside, and I will get AC inverse times e to the AC minus I into BC 2 times Vn. All right. So, therefore, x of n plus 1 is e to the AC x of n plus AC inverse e to the AC minus I times BC times U of n V of n. Does it make sense? And thankfully, y of n is simply y of t is nothing but a linear combination of the states plus a linear combination of the inputs, which means that we must also follow that the samples of y must simply be the same linear combination of the samples of the states plus samples of the inputs. So, this will simply be Cc x of n plus dc u of n v of n. Does it make sense? So, you now compare this to the standard formulation for a discrete time system, which is x of n plus 1 is A d x of n plus B d times u and v, and y of n is C d x of n plus d d u and v. So, if one wants to find the state space representation of a discrete time system, right, which is being mimicked by the continuous time loop filter, as long as the two inputs can be modeled by first order held waveforms, right, one can simply replace or the equivalent discrete time A matrix can be obtained from the continuous time A matrix by e to the AC. Okay. Similarly, BD is AC inverse e to the AC is nothing but AD minus I times BC. CD and DD are simply CC and DC. Okay. So, the poles of the loop filter are nothing but the given AC, they are nothing but the eigenvalues of the A matrix. So, when we were discussing this in the context of loop filter design, we said that if a discrete time filter, if the discrete time loop filter prototype has a pole at P1, the continuous time loop filter must have a pole at ln of P, right, and that is being reflected here also, because the eigenvalues of AD and the eigenvalues of AC are exponentially related, because AD is exponential of e to the AC. You understand? All right. So, once given AC, BC, CC and DC, the corresponding discrete time state description can be found. So, one can therefore use a discrete time simulator to run all your simulations. You understand? Of course, this one thing I would like to bring to your attention is the fact that you must make sure that the assumption of input being modeled well by a first order held waveform is valid. Okay. Now, what if you want to, after all, one of the advantages of continuous time delta sigma modulation, as we mentioned in the very beginning, is the fact that there is implicit anti-aliasing, correct. So, what if one wants to check this out in simulation? Can one put, using this formulation, can one put a sinusoid at Fs ideally if you take a real continuous time sigma delta modulator and put in a sinusoid at Fs, what should the output sequence be? It should be 0, correct. But if you emulate the sinusoidal behavior, the continuous time behavior by an equivalent discrete time system, right, the underlying assumption behind that emulation is that the input is varying sufficiently slowly that it can be modeled fairly accurately by a first order held waveform. So, this simulation technique that we have just discussed will not be accurate for excitations which are high frequency excitations. These are high frequency inputs are perfectly legal inputs to have in a continuous time delta sigma, right. But this simulation technique is not good enough for that. One way of doing this is to deliberately assume that the loop filter is sampling at a much higher sampling rate than the quantizer. You understand? So, instead of assuming that the loop filter samples are needed only at 1 hertz, if you say I will compute the loop filter samples not at 1 hertz, but at say 32 hertz, right, which is still better than computing the loop filter output for all time and only taking one sample, right. If the loop filter is sampled at a much higher rate than the sampling rate, then at least intuitively you can think that for inputs as high as about 16 hertz, the output, at least the whatever, you should be able to recover the input from the samples. In other words, there is no aliasing in the simulation, all right. But that is something that I will not cover in this class. But as far as low frequency inputs are concerned, this is a easy way of implementing the entire simulation, right. So, maximum stable amplitude, stability, all this stuff can be simply gotten from a simulator intended for discrete time modulator design. Well, again, it depends on what accuracy you want. You already know what the error is, right. The error is the difference between the the continuous time waveform and the first order held approximation, right. So, you know, for oversampling ratios of about 32 or so, I think this still, I mean, visually you can see that it's kind of okay, right. But I mean, it particularly fails when you are trying to simulate really high frequency inputs into the modulator, which is a very common scenario for CTDSM operation, right. The fact that you do not need an explicit anti-alias filter means that now somebody will say, hey, why do you just remove the filter and then I am going to put in an input which consists of all sorts of arbit tones, right. But then your modulator, I know, has got free anti-aliasing. So, none of that stuff will alias into my signal band, right, and stuff which does not alias into my signal band will get knocked out by the decimation filter in the digital domain, which you need anyway, you understand. So, you know, the input content into a modulator like this can be very hostile. It need not necessarily be confined to the signal band, as would be the case for a discrete time delta sigma modulator. Okay, does it make sense? All right. So, as a final point, you can go through the similar analysis. Let us say the DAC was not a non-return to 0 DAC, but only a return to 0 DAC. What would change in this approach? What would change in the approach? Yeah, what do you think will happen to this guy? That will remain the same, right, okay, because the poles cannot change with the input. The only thing that is changing is the nature of the input. Okay. Now, as far as the input is concerned, you can still model it as a first order held waveform. So, the BC1, right, will still remain an expression which looks similar to this. Okay. The only thing that will change is BC2, I mean BD2, and the change will be, instead of integrating this from 0 to 1, you integrate from 0 to half, that is all, correct, and you will get a different expression, okay. But that is about the only change. If you have an arbitrary pulse shape, of course, you have to compute the integral, all right. You may, I mean, you may not be lucky to get a nice clean closed form expression like this, okay. All right. So, now let us start getting into implementation details. I mean, now we have seen, you know, all possible, I mean, all the issues relevant to the within quotes system design of the loop. We know how to, given a noise transfer function, we know how to design the loop filter, right, how to get its coefficients, what to do when there is excess delay, what to do when there is jitter, what to do when the time constants vary. We also know how to scale the output such that none of the integrators you know, prematurely limit the performance of the modulator, and we know how to simulate the loop given the loop filter properties. So, the next thing to do is start looking at how one might implement some of these circuits, all right. So, today we will take a very top level view of implementing the integrators, all right. So, there are several possible integrators. I am only going to discuss you know, macro model type approaches in your analog integrated circuits class. You will learn, or you have learnt, how to design a good op amp, okay. So, the op amp is the workhorse of a lot of analog engineering. So, from your earlier classes you have probably seen this as an example of an integrator. So, if the op amp is ideal, VO by Vi is nothing but minus 1 by SCR. Now, clearly no op amp is ideal. So, in practice there are several ways of implementing the op amp. Okay. One can realize an op amp as one way of realizing the op amp is to think of it as a voltage controlled voltage source with a very large gain A. All right. Unfortunately, it turns out that in CMOS technology, if you try to realize an op amp as a voltage controlled voltage source, the signal swing that the op amp can support at its output is severely constrained. All right. I mean, have you all been through two stage op amp design at this point in analog ICs? Yes, no? Okay. So, it turns out therefore that if you have, if you make the op amp a voltage controlled voltage source, by definition the output impedance has to be small. If the output impedance is small, it means that internally what must you have, what kind of single transistor stage gives you a small output impedance? You need to put a voltage controlled voltage source inside, which is basically a source follower, and it turns out that when you have a source follower, you can you know that there is the output voltage is one threshold voltage plus one overdrive below the input, correct, which means that on the lower side the output voltage can go almost to the negative rail, but on the upper side you will be constrained because not from this transistor, but the transistor driving this, which is most likely a PMOS device, and this can go a little below supply, right, one overdrive below supply, which means that this voltage can go only 2 overdrives plus a VT below supply. You understand? So, instead of thinking of the op amp as an ideal voltage controlled voltage source where the gain tends to infinity, that is what one normally thinks of an op amp as, right, as a voltage controlled voltage source with a gain which tends to infinity. One can also think of an op amp as a voltage controlled current source where the GM tends to infinity. All right. Okay. So, many the advantage of this as I said is that it does not have the problem of losing voltage swing because you need a voltage controlled voltage source in the form of a source follower inside. Now, if you had a buffer, if you had a voltage controlled current source, then one way of realizing an integrator is to choose this to be GM, okay. And please note, as I said again, that the GM must tend to infinity. So, this Such a 3 terminal element where the transconductance tends to infinity is what is called OTA, which stands for operational transconductance amplifier. Okay. And of course, it is not possible to get an infinite GM. In practice, GM will be finite, which means that the integrator will not give you, if GM tends to infinity, the input output relationship will be minus 1 by SCR again. Is that clear? If this GM tends to infinity, okay, this the transfer function will tend to minus 1 by SCR, and what will be the output impedance? If this is an op amp, is a voltage controlled voltage source, what will be the output impedance? 0. Now, if I use an OTA instead of the op amp, what will the output impedance be? Okay, please think about it. We will continue in the